Hello everybody. In the previous session we have seen the concept of zombie and the concept of orphan processes. We have also seen how the multiple forks when implemented in the program, how the program behaves. Today we'll see some examples related to fork, related to zombie and related to orphan processes and multiple forks. Look at this program. In this I fork a child process. The child process is created using the fork call. The fork, when executed by parent, returns the child PID. Fork, when executed by child, executes 0, returns 0. So we have both the cases. This is the case that is going to be executed by the child process, and this is another case that is going to be executed by the parent process only. And the rest of the code after the switch statement is going to be executed by both parent and child. Look at the parent process first. The n variable which I have created as a local variable is in the stack segment. The n variable is assigned to 20 by the parent process, and the n variable is assigned to 10 by the child process. As we have learned earlier, the n variable will not be overwritten by the child process, but both the parent and child will have different n variables according to the concept of copy and write. Both the n variables will have space occupied in the same stack segment, will have the same logical addresses, but will have their own local variables. Okay. The parent will print its PID, PPID, and the return value that is returned from the fork, which will be the child PID. The child process will print the PID, PPID, and the value of fork return, which will certainly be 0. The child initializing variable n to 10 and parent initializing variable n to 20. After the switch statement is over, the control goes out into the for loops. Now just try to answer me. This for loop will be executed by parent or child or both?
So for loop sets by both.
Both parent and child.
Sir, both.
Yeah, both will respond. Both will execute the for loop. Now the for loop is being executed from I is equal to 0 to I less than n. Can you tell me, if both are executing this for loop, then this for loop will be executed by parent how many times and will be executed by child how many times? Answer me in the chat. Don't switch on the microphone. People who are silent spectators, please participate here and tell me in the chat how many times the for loop will be executed by parent and how many times the for loop will be executed by child. I'm really impressed with the way Amardeep responds to my queries. If you keep on responding like this to me, I see a great future for you, Amardeep. Yes, all of you are correct. Very good. Now the loop will be executed by the parent 20 times and child 10 times. And every iteration there is a delay of 1 second. In every iteration both parent and child will print their own respective PIDs and the parent PIDs. When the parent will execute this statement 20 times, the parent will print its own PID and the parent's parent, that is shell's PID. When the child will execute this for loop, child will execute this for loop 10 times, child will print its PID and its parent PID. After 10 iterations, child will be out and print the end statement, but parent will continue to execute till 20 iterations. So for the iteration number 10 onwards till the iteration number 20, the child process would have finished its execution but would not be terminated, because any process cannot commit suicide. Any process could be terminated only and only by its parent process, isn't it? Because the parent process here is busy executing in its for loop or sleeping. The parent process is not getting any CPU cycle, free CPU cycle, idle CPU cycle. Therefore the parent process will not be able to execute the child's termination section. As a result, the child will continue to stay in the process table as a zombie process until unless the parent process executes in the iteration number 11 to 20. After 20 iterations, the parent process will also come out of the for loop and execute the end statement and exit statement in line number 43. When the parent will execute exit statement, then as part of exit, the parent will check its zombie process and execute the termination section and terminate the zombie process, and then the child process will terminate, and then the parent process will request its own termination. Then the parent process will terminate it by the parent's parent shell by executing the parent's termination section. So let's see how it works. Demonstration of this program. If you do not understand, please do not hesitate to ask me the queries. Compiled and executed. Let me come here and do all executing programs. Now I am going to run the program. Both parent and child start executing there in the iteration. You see both parent and child, parent PID 176, child PID 177, both executing. After 10 iterations, child will be over. Child is over, only parent is executing now. See, now the child process, that is 77, have become zombie, and it's a defunct process. It has nothing to execute but living in the process table as a defunct process. After 20 iterations, when the parent is also over, you see both the parent and child are gone. Did you see? Let me do it once again. Both parent and child executing. There you see process number 189 and process number 190, both executing. After 10 iterations, child will be out of for loop and will finish execution, and child will become zombie process, defunct process. After 10 iterations, 20 iterations, when the parent will also be over, parent will execute its termination section, and both parent and child will be terminated now. Zombie process. Okay. Again, the same program, but slight difference. The difference is that the child process executes for 20 iterations and the parent process executes for 10 iterations only in the for loop. Now, after 10 iterations, the parent will go. Child will become orphan and continue its iteration number 11, 12, 13, 14, 15, 16, 17, 18, 19. Those last 10 iterations, child will execute as an orphan process. If the child is an orphan process, then what will the child print in its PPID? Because the parent PID is gone. And the parent PID, parent's parent is shell, which would have certainly executed the termination section of the child process and would have terminated the child process, parent process, sorry. The shell would have executed the termination section of the parent process, and the shell would have successfully terminated the parent process, making the child process as orphan. When the child process becomes orphan, what is the PPID of the child process and who terminates the child process? Both parent and child starts to execute and will execute till 10 iterations. After 10 iterations, the parent process will terminate and the child process will continue executing alone. The parent PID was 95 and child PID was 96. When the 95 parent process is over, then the child's new PPID is parent PID is 1671. The child process became the orphan process. Inside Linux system, there is a process called system D. The system D process adopts the orphan child process and becomes its parent. And when the child process finishes its execution, then the system D process will terminate the child process, the system D process, which you've seen in the last class. Adopt so many orphans, isn't it? And the process is over. Let me run this once again. Yeah, both parent and child executing 330 and 331. After 10 iterations, parent will go, 330 will go. Oh, 330 gone. Now 331, child is the only process that is executing as an orphan that has been adopted by the system D process. After 20 iterations, the child will also go. isn't it? Orphan processes. The concept of orphan. You understand that? But look at this. There is a problem here. The shell is not showing the prompt. The shell here is not showing the prompt because the shell have started two processes in the hierarchy. A parent process and the child process. The shell maintains the count of number of processes executed. Within that count, it sees that 20 processes, two processes have been started, a parent and a child. The parent process finished at this point, and its termination section was executed by the shell process. So the count decrements from 2 to 1. The child process was adopted by the system D process. It all happened like this. So there was a parent process executing. The parent process, the shell, suppose this is a shell executing. The shell created the parent process. The parent process created the child process. And the parent process finished before the child process. Suppose this is shell. This is parent. And this is child. Okay. At this point, the parent process finishes its execution, and the parent process termination section was executed by the shell, and the parent process was properly terminated. Gone. The moment the parent process was gone, the child process was immediately at this point adopted. By system D. At this point, when the child process finishes its execution, the child's termination section is executed by the system D process. And the child process also gets terminated, but there is no link with the shell. Therefore, nobody informs the shell that the child process is also finished execution. The shell keeps waiting that there is one more process executing, maybe executing in the hierarchy of processes invoked, and therefore shell is in a wait state. This is a problem and very inconsistent state. When the parent process finishes its execution before the child process, there is a level of inconsistency in this. Okay, so we have to prepare to solve this problem. This problem is solved by providing some kind of syncing between the parent and the child process, such that the parent process should not finish its execution before the child process. Now suppose it is done like this. Suppose this is your parent process executing. Parent process creates a child process. The child process executes here, and the parent process finishes its execution before the child process at this point, and child will finish its execution here. This is the termination section of the parent process, which has to be executed by parent's parent, and this is the termination section of the child process, which will be executed by child's parent. This is the parent process, suppose PID is 100. This is the child process, PID is say 101. Now at this point, when the parent process terminates, the child is becoming orphan. We have to prevent it first from becoming orphan. Second, we have to bring consistency so that the shell doesn't hang, isn't it? For that, what we have to do is we have to provide some kind of pause here to the parent, some kind of that the parent should stop and not issue its own finishing of execution. Parent should not finish. Okay, it should pause here. The parent should pause. The parent process should have capability to pause. The parent process should have some capability to pause its execution anytime until a child process finishes its execution. So the parent will go into pause and will stay in the pause unless the parent continues its execution and the parent process finishes its execution. Till that point, the parent process should stay in the pause state. Pause. Okay. Well, this is implemented in Linux system programming using a system called wait system call. The wait system call will take argument, which is a pointer to pointer of type void, and it will return child PID of the process which just finished execution. The wait system call. How it works. The wait system call will pause the execution in parent process. Okay. When the child process will give exit call with some exit code. The execution will proceed in the parent process at this point. Okay. So we'll see this. We'll implement this and see how it works. The wait call will return the PID of the child process that just gave exit call with exit code. Okay. About the argument, I'll tell you later. So let's see how it works. Wait system call. 4 programs starting. The PID and the PPID printed. 4 call given. Child process created. In the switch statement, child will execute its own block, n is equal to 30. Parent will execute its own block where n is 15. Both parent and child will go into this block as usual. Okay, parent will execute in this iteration 15 times because the n is 15 for the parent, and child will iterate till 30 iterations. Let's make it little small. Let's make it 10 and this make little 25. Now, after 10 iterations, the parent process will come out of this block, and the parent will print its PID and it will say past iterations. Then we'll check the return value of fork. The fork return value. Let's not call it PID. Let's call it fork return or only return. The return value of fork will be captured in RET. If the return value of fork was a positive value, not 0, then this block will be executed, and this block will be executed only by parent and not by the child, because the return value of fork from the child was 0. So therefore this block will be executed only and only by parent and not by the child. What the parent will do is, parent will give the wait call and go in pause, will not do anything. The child will continue iterating till the 25th iteration. After 25 iterations, the child will also come out of this loop and will print its PID past iterations. Then the child process will say, check this loop. The child process will not be able to give true condition, not go into this block. Child will come here and say process child PID terminating, exit n. The value of n for child was 25. So child will give the exit code 25. The moment the child process will give exit code 25, the parent process that was in wait will come out of wait. Wait system call will return the child PID of the child that just now finished execution, and the wait will say that parent PID past wait call and will print the child PID. This is just a simple demonstration of how the parent process waited for the child process to finish its execution. Okay, let me demonstrate this to you how it works. There is another thing, argument, that we will see in the next example. Let's try to execute this. Concepts are very important. Don't leave anything to be doubtful. Redeclaration of RET. Did we declare RET twice? Oh yeah. Why did we declare twice? Now let's compile it. Oh no.
Good evening, sir.
Very good evening. Very good evening. How are you?
Sorry sir, बिल्कुल मिस हो गया था. माइंड से स्लिप हो गया.
PID undeclared line number 14. Yeah, this is RET actually now. Executing. Both parent and child executing for 10 iterations and 25 iterations. Parent 10 iteration, child 25 iteration. After 10 iterations, parent will go in pause and only child will execute. See, past iteration. Parent has paused. Only child executing. And child will execute till 25 iterations. After 25 iterations, child will give the exit code. Then the parent will come out of wait call, out of pause, execute the termination section of child and terminate the child. And then the parent process will also terminate. And that's what happened here. Let me execute it once again for you. Both parent and child execute. Parent for 10 iterations and child for 25 iterations. After 10 iterations, parent will come out of loop and go into pause using the wait system call. There it is. Past iteration. Parent is in pause, is in sleep state on the wait. Child will execute till 25 iterations. After 25 iterations, child will give the exit call, and then the parent will capture the exit call, and parent will execute the termination section of the child, terminate the child, and then the parent will also get terminated. Notice, the shell is also happy. Shell is not hanging this time, like the previous case. Executing it once again for the third time. Watch both parent and child executing. Both parent and child executing. Parent has gone to sleep state. Parent did not terminate like before. Child was not orphan at all. When the child finished 25 iterations, then the parent come out of pause, terminate the child, and it also gets terminated. Here, everything is in sync. Shell is also happy. Wait system call. Okay, let's have a look at another example. The return value of wait, which we did not consider last class. Again, the child will iterate for 25 iterations, say 20 iterations, and the parent will iterate for 10 iterations in the loop past the switch statement, and then FRET will be checked by the parent and child. Only parent will be able to enter in this block because their fork return value will be positive for the parent and 0 for child. The parent process will go into wait system call. Wait will return the child PID. Okay. Also notice this. We have declared a RET. Integer. I have given address of integer. So it's a pointer. Small correction here. This will not be pointer to pointer. This will be pointer to pointer in threads, not in processes. It will only be a pointer. Now I have given an address of integer, means it's integer pointer. When the child process finishes its execution, it gives the exit code like this. When the child process will finish, the child process will finish with this statement. Exit, some exit code, say N. Okay. The parent is in wait using the wait system call, and there is a address of, there is some pointer here being used by the wait system call. The parent is in wait, and the child will issue the exit call. When the child will issue the exit call, then this exit code, that is N, will be returned from the child process to the parent process. Unlike functions, where the return value of the function is captured by the calling function in some variable, the parent and the child process cannot do that, because the return value that will come, N, will be returned and captured here. In some location, which is certainly not in the stack segment, not in the code segment, not in the data segment. It is kept at a separate place, which I'll tell you later, in process context only. So, the exit code that comes from here comes and gets stored at some location outside of segments. The exit code given by the child process is not stored in any segments. So it could not be accessed using any pointers, because when a pointer will try to access something outside the code segment or data segment, it will end up in segmentation fault. So therefore the exit code that is given by the child process could not be accessed by any pointer. And look at this, what we are doing. We are trying to use this pointer PTR to refer to the exit code, isn't it, and fetch the exit code. But according to the concept that I have given here, this will not be possible. Exit code cannot be simply fetched by this. We are trying to print this exit code. See this RET? You are trying to print this exit code. See what happens. The exit code given by the child process is n, and the value of n for child was 20. Run. Both parent and child again execute just like before, and child will iterate for 20 iterations, parent will iterate for 10 iterations. After 10 iterations, parent will use the wait system call and go in the pause state. Child will continue its iteration. As you see now, the child will continue its iteration till 20 iterations. After 20 iterations, child will give the exit call, exit n. N is the exit code which is supposed to be captured by the argument of the wait system call, but it will not be able to capture. See, the exit code is coming some garbage value, 5120, isn't it? So exit code could not be fetched like this. We have to use two macros to fetch the exit code. Okay, one is w exit status, this one, and another is wif exited. Let me explain this to you here. The exit code given by the child process is not stored in any segments, so it could not be accessed using any pointers. Okay, the solution is let's talk about this exit code first. This pointer is going to refer to a location where the exit code of the child process could be fetched from. Okay, now as this value, the exit code of the child, is not in the code segment, is not in the data segment, therefore it could not be accessed directly. Okay, you need to use two pointers. The pointer is going to refer to a location where the exit code of the child process could be fetched from, but this location is not accessible directly. The exit code of the child could be fetched using a macro called WIF exited and W exit status. Now what are these two macros? Just have a look at these two macros here. WIF exited. It will take the same variable as an argument. It returns true if the child process finished its execution successfully without any errors. Also, that its exit code is a relevant value. Okay, because the child process has executed normally, therefore its exit code is a relevant value. Okay, W exit status. Another is W exit status. This macro it returns the exit code. So what we have done is, in our program, the exit code is going to be 30, say 20 for the child and 10 is for the parent. After the switch is over, both the process go into the loop where the parent process will iterate for 10 iterations and the child will iterate for 20 iterations. The parent will come in this block and will go pause on wait. When after 20 iterations, child will come out of these iterations, child will print past iterations, child will not go into this block because the condition will be false. The child will come here and say process terminating and the child will give the exit code which is 20. After that, the parent process will come out of the wait and try to fetch the exit code using WIF exited RET, which will tell you if the child process have terminated normally and the exit code is the relevant exit code, then it will return true for if. If true, then fetch the exit code using W exit status. Now you will get the correct exit code. You will see here. Both parent and child executing for 20 and 10 iterations, 10 and 20 iterations, right? After 10 iterations, parent will go into pause now on wait. Child process continues its execution. After 20 iterations, child will give exit code which will be fetched by the parent process using wait. There it is, exit code 20. Did you see that? So this is how the parent and child are not only in sync, but the parent would have created the child process with some purpose, and that purpose will be resolved by child giving some response. Parent will need that response, and the parent issues pause wait system call where it waits for the child to give the response, so that when it have that response or some data calculated by the child process, parent may need it for some further processing. And this is the scenario where it works like this. Okay, so this is parent waiting for child process wait system call. Have a look at another. Here what happens, Both parent and child execute. Child is finishing before the parent process. Child exit code is 15, n is 15, parent n is 30. So child will execute 15 times, iterate 15 times, and parent will iterate 30 times. After 15 iterations, child will come from the iterations before the parent and will say past iterations. Child will not be able to enter this block because the condition is false. Child will come here and give the exit code. Exit code for the child is 15. Meanwhile, the parent will continue executing the after 30 iterations, parent will come and try to wait for the child, but the child process have already finished execution, and the child exit code will be child PID will be returned back, and immediately it will not be able to stay in wait. It will come out of wait immediately and check if the child had terminated successfully in the past, and if yes, then it will fetch its exit code. What I am trying to show is that the exit code of the child process could be fetched even in future in time. The child process may have terminated in the past. Let's see how it works. Does it work like this? Here it is, both parent and child executing normally. After 15 iterations, child will come out of the iteration loop and give the exit code and go. But it will be held zombie. See, defunct zombie. Third last line. Later on, its exit code will be captured by the parent and will be terminated properly. But the exit code could be captured in future also, even if the child have finished execution in the past. There you see the exit code 15 captured. Okay, so that explains to us one concept, that in the process context, there is a small table maintained in which you will have details about the process groups and the child and the thread groups.
सर वॉइस ब्रेक हो रही है सर आपकी।
Two different, मेरे को फिर व्हाट्सएप कॉल कर लो। Two different tables are maintained in the process table other than the 3-4 segments that we have discussed. These two tables are called the process identification table, which identifies the child processes, parent processes, siblings, and all these things. It will keep track of all those things. And it will also maintain another table called thread group identification table. Threads we'll learn later. Okay, so it is in this table that the exit code of the child process was returned, captured, and stored and held, which was later on used by the parent process. Right. So this is the concept of zombie, concept of orphan, and the concept of wait, and the exit code fetched using WIF exited and WExit status. Okay, this is how the fork works. Any queries you have related to today's session, you can ask me now. You may ask me now. Very nice. So I hope you have understood the concept nicely, and look at the documents, notes that are prepared for it, and consolidate your concept by reading the notes. Give a casual reading to this and try to demonstrate the concepts through programs. I will continue my discussion a little bit more on fork in the next session, then we'll move on to the next topic. Till then, bye-bye.